Welcome back. So we saw in the earlier modules basic way to approximate the continuous differentials, either if it is a first order differential or a second order differential, using certain difference equations. So let's use those differentials to model a simple one-dimensional wave equation. So we'll start with a simple one-dimensional wave equation represented by this particular equation. So what we have is we have a second differential with respect to x multiplied by certain quantity, let's say the constant is k square, and is equal to the second differential of u with respect to time. So what we are having is a simple case of a one-dimensional equation. It could have a physical meaning. We are talking about a value that is changing only in x with respect to time. It's a one-dimensional form. Here you say that time equal to 1, time equal to 2, time equal to 3, time equal to 4, and so on and so forth. And obviously we have to give certain boundary conditions. Before talking about the boundary condition, let's only look at differential equation and try to transfer this differential equation into finite difference equation, because we have got already the approximation for d square u by dx square and also for d square u by dt square. So using that approximation which you saw in the earlier slides, so we will use those approximation here and we can write them directly in the form which is given here. So we have the k square and we have the approximation, the central differencing approximation with respect to x for the second differential is equal to the central differencing approximation with respect to t. So what you have got here is a central finite difference equation, and this is when you are rearranging the terms. So here I have the value written in terms of time, the j components represent time. So what I am interested is I wanted to compute the value at j plus 1. Remember in the slides before we said that we are interested in computing the values, the unknown, at time j plus 1. So I need to get a simple equation which will give me the values of the variable at time I j plus 1 using the values which are before. So what we have got now is finite differencing formula using the central differencing scheme. So using this particular expression we can reorder this terms such that we bring this I comma j plus 1 on the left hand side and write the other terms on the right hand side. What we get here essentially is a term, an expression for u of I comma j plus 1 is equal to certain value on the right hand side. So this value totally depends on the value of u at time j or earlier terms. Remember j is the time coordinate. So if we substitute the value r for the term here which is a constant k delta t by delta x square, so what we get essentially is a compact form of writing u of I comma j plus 1 as a function given here. So what we have is we have a term that is r sitting here and we have certain multiplication. So these are nothing but weights. So what you see as the coefficients are nothing but weights. So here the weight for u of I comma j is 2 1 minus r. The weight for the component I comma j minus 1 is minus 1. Similarly the weight for both the terms I plus 1 j and I minus 1 j is r. So if you take a very simple straightforward condition where we assume the value of r is equal to certain values. So obviously the value of r cannot be any value, it has to be certain values in between certain bounded quantity. So what that bounded quantity is going to be is something that we will see. We will see here the formulation what we have here is an explicit formulation. As I told before, we are computing the value at j plus 1 purely based on the value at j or j minus 1 steps. So the role of r is quite interesting to notice. So the value of r is bounded between certain two values. As I said, it is definitely more than 0, but it could be either 1 or less than 1. So based on this bounded value we can have two cases. So the case number 1 is r is just less than 1 and it's more than 0, and the second one is r is exactly equal to 1. So when we have the value of r exactly is equal to 1, what we can see is we have certain terms that are getting cancelled. The term which is here 1 minus r, all these terms will get cancelled for r is equal to 1 because 1 minus r will become 0. So this term will completely disappear, whereas the other terms will stay. So that is what you will see. What it means is, if you see the 1 minus r term here is purely based on the weight that is for the coordinate point I comma j. So if I put r is equal to 1, my value of the function at u of I comma j is not important, but if I put r is less than 1, my values at I comma j is also important. That is what you will see pictorially in this particular graph. If I wanted to compute the value of various time steps and I set the value of r is between 0 and 1 and strictly less than 1, what I say is my value at this point can be computed using the values at all these neighboring points including I comma j. But the moment I put r equal to 1, the value at the center, which is the weighting of 1 minus r, will become 0, is not important, it will be purely based on the values here. So this is the way we are going to compute the values of u at various time steps, and we are going to take a very simple problem represented by this particular expression given in the slide. So we are interested in a problem where it is nothing but the same problem, but what we have done is we have put k equal to 1, partial differentiation with respect to time, second order partial differentiation with respect to time is equal to the second order partial differentiation with respect to x. And we can write this particular expression in a much more compact simplified notation like here. And what we said before is, in order to run the simulation we need to set certain boundary conditions. So first let's look at the boundary condition. So the boundary condition says the value of u at time t, any time t, but the boundaries are 0 and 1. Remember, in the problem what we had before, we said the value of x goes from 0 to 1. So in this case, if we say this is the x axis and this is the y axis, and the x axis is the value that goes from 0 to 1. So this is 0, this is 1. And similarly, the value in the y axis is the time axis, and it goes also from 0 to certain value, let us say t. And obviously we are talking about certain space discretization and also time discretization, which we will see now. So what we are saying now in this particular condition, it is called Dirichlet boundary condition because it is named after a scientist Dirichlet. So when we say the value at x0 is given for all time steps as 0, and the value of u at x equal to 1 for all time step is also 0, and that is what we have represented mathematically in this particular expression. And since it is a second order differential equation, we need to set two initial conditions, and those two initial conditions are, for all time steps we set the boundary conditions, but for all spatial steps at time equal to 0 we set the initial condition. It is initial because time is equal to 0 here. So at time equal to 0 at x coordinates, the u value is given by sine of pi x. Similarly, the first differentiation with respect to time for all spatial steps but time equal to 0 is given to be 0. In other words, the value of u at time step equal to 0 is given by sine of pi x, and the value of the differentiation with respect to time at time step equal to 0 is equal to 0. And these are the two initial conditions which we have to satisfy. Without worrying too much, we can already get the analytical solution of this particular expression, which is given by the value here. So the analytical solution for that particular expression is given by the value sin pi x and cos pi t. So it's a multiplication of sin pi x and cos pi t. And what we are seeing now is we can use this as a reference solution because we know the analytical solution, but we can also use the finite difference formula to compute the value of the expression in a compact form as given by this particular expression. What we have got now is the value of u of I comma j plus 1 is equal to the value given by the right hand side. And obviously we said we have the value I belongs to the x coordinate and j belongs to the time coordinate. So if we put I and j certain values, we can already get the values for the initial and the boundary condition. That's what we are going to do now. We put j is equal to t equal to 0, we can get the value for the first derivative given by this expression, and we know delta t cannot be 0, so only the numerator can be 0, and this is the initial condition which is given. We said for u of t at the initial time t equal to 0 should be 0, so this particular expression should be 0, which leads to the condition that the numerator term should be 0. In other words, u of x comma 1 should be equal to u of x comma minus 1. And recall that we use the value r is equal to k delta t divided by delta x square. So in our case k equal to 1 and delta t is equal to delta x. For simplicity, it need not be like that. So for the sake of simplicity, we said delta x and delta t are equal. So we get the value r is equal to 1. And this particular problem what we have in this slide is symmetric about the point x equal to 0.5. That's what we see here. So the problem is symmetric about the x equal to 0.5, and that you will see when we do the simulation in the next slides. So what we set is we set certain value for delta x and delta t, and since they are equal we say it's 0.1 for simplicity. Obviously we can change the value of delta x and delta t to different time step and we can compute the values. So if we set it is equal to 0.1, what we will get is an expression for u of x, and we can compute the values accordingly, and we will use the value r equal to 1. Obviously when r is not equal to 1 we get a different set of expression. This particular expression is only valid for r equal to 1, and now we will go into the numerical simulation of this particular problem. So what we will see now is the Matlab code, and we also will compare numerical result, and throughout this course we will be using Matlab to showcase or demonstrate certain proof of ideas or certain numerical schemes. So now we will focus on certain problems using Matlab. We know the explicit formulation is given here, and we also know the analytical solution. So we are going to set certain values here. The values I am setting here is I am making sure the r value is going to be 1. So and I am going to change the value from, let's say I am going to go from 0.5 to 0.1 to 0.01. I am going to refine the mesh from 0.5 to 0.1 to 0.01, and for this I will have a finite difference expression using the central differencing scheme, and this is what we are going to see in the Matlab code. So let's look into the Matlab code itself. So what you have got now is a Matlab code for solving the problem represented here. U double t is equal to u double x, and this is we are setting certain values, and let's say we are starting with delta x is equal to 0.5, and internally we have set delta x is equal to delta t. So based on the spatial resolution we are choosing for delta x, our value of the resolution in time step is also going to be changed because it is related through this expression. And we set r equal to 1, and we have the value of u, a constant wave, So we say the value is of u will be 1, the maximum value, and we are computing the values at different time steps using the equation here. So we are initializing the grid in this step, and we are initializing the conditions and the reflections. So what we are interested is in computing the value at different time steps and spatial steps. So the value of the x1 is only computed until 0.5. As I said, the equation itself is symmetric, so we are only computing the value only half of the field. So that's why we are having the expression here divided by 2. Since the problem itself is symmetric, we are only computing half of the field, and this is simply because we need to reduce the computational cost. This is a very simple one-dimensional problem. The computational cost is not that important, but as you go in higher order, such simplification based on the geometry and based on the problem itself is going to make our computation time shorter. So we are initializing the conditions and we are computing the value, and the value here is x1 is the same expression what we have got in the finite differencing form. So here we are using the value to compute the value at different time steps and the spatial steps. So the rows and columns are the time steps and the spatial steps respectively, and we have the value of x1, which is the due to symmetry condition is only half of it, and once we computed this, we are using the symmetry condition to recreate the entire field. So x2 is basically the value that we computed before, and it has the other term which is due to the symmetry condition will also come into play. And the value here ax2 is the analytical solution which we know, which is computed based on the value which we know. So this is the sin pi x and the cos pi x term. So we are computing the value of ax2 here. So the reason why we are computing this is we can see what is the value that we are getting through numerical value and what is the value we are getting from analytical expression. So here we are plotting two figures. The figure 1 is a numerical result for the hyperbolic problem. So the kind of problem we are simulating is called hyperbolic. We will describe this at a later stage. It's enough to know that it's a hyperbolic problem, and the value that we are plotting in the figure 2 is an analytical solution, and once we run the simulation we will see the value is going to change as a function of delta x and delta t. So the del x I am initially choosing 0.5, and the value of x goes from 0 to 1, and this is a very coarse grid. So when we run this code, particularly the way we have structured it, we get two figures. The first figure will be the value of the numerical result, and the second figure will be the analytical result. So it's important to know what this analytical result means so that we can compare the analytical result with respect to the value that we compute using numerical method. So this is an analytical result. The analytical result is based on the analytical problem, and the value is symmetric across x equal to 0.5. You see that the value whatever is on the right hand side to x equal to 0.5 is the same as the value that is on the x equal to 0.5 left hand side. So that's why we only computed the value until one side and then we replicated the value accordingly. Similarly, it's also interesting to see the value is also symmetric across the time step, but that's not important, and the numerical simulation should be something that is similar to this, but obviously with certain errors. And it's important to see the analytical result has the value goes from -1 to +1. So +1 is the dark yellow and -1 is the dark blue, and we will compare these results for various time steps and also various spatial resolution. So initially we will compute this value for x equal to delta x equal to delta t equal to 0.5, and we will compare it with the result of analytical solution. Obviously we expect the result to be not good because delta x and delta t equal to 0.5 is a very coarse grid, and we will improve this by refining the grid to 0.1 instead of 0.5, and then we will compare the result of the solution, numerical solution, with analytical solution, and we will also do it for delta x equal to delta t equal to 0.01. So let us take now the example of delta t equal to delta x equal to 0.5. So here I am going to use the value 0.5, and when I do it 0.5 and I am running the simulation, what you see here are two figures. The first figure is the numerical result and the second figure is the analytical result. As you can see, the numerical result is a poor representation of the analytical result. You see the values on the left and right having some similarity but not exactly. You see that there is a maximum at the extreme point on time axis, and there is a minimum at the middle, but again it is not very good. So let us see if I am improving this by going even finer in the grid space. So I will go from 0.5 to 0.1. So when I do this, I expect the value of the numerical results to improve. So let us see what happens. So this one should change, and as we expect, this is changing. As you can see, the value is no longer simple 2 points, but it is also showing certain nice behavior, and obviously you can still see the numerical error, and these are like what you see as pixel figures here. And let us now refine the grid even finer. Let us go from 0.1 to 0.01, and we expect both the numerical result and the analytical result to be very similar, and let us see what happens. And as you can see, the value of the numerical result, which is on the right hand side, is almost equal, in fact very much the same as the analytical result. And obviously there is still some error, but this error is so fine it is not visible to our eyes, but if you compare the values to the decimal points, you will still see there are some errors, but this is more than enough for practical purpose. So with this, we are able to compare the analytical result versus the numerical result. So we have come to the end of this particular module. We have started with a simple wave equation, and we have showcased how we can do this stage by stage. We have set r equal to 1 in this case. We can also set r equal to any value between 0 and 1, and we are able to get a similar result. So what we have covered so far is we have covered basic expressions for modeling a finite difference one-dimensional wave equation. We have also showcased certain problems, and next modules what we will do is we will look into accuracy and also stability of the numerical method. So with that being said, we will come back again and we will focus on the further techniques in finite differencing. Thank you.